Okay, by this time you are familiar with the TS diagram for various reversible thermodynamic processes, and we concluded that the isentrope in a TS diagram will be always a vertical line, the isotherm will be a horizontal line, and isobar and isocore will be curves with the isocore steeper than the corresponding isobar. Now, using these ideas, let's try to draw the TS diagram for the gasoline and diesel engines. Now, in order to make our discussions better and for a comparison purpose, I have reproduced the PV diagram for the gasoline engine and the diesel engine at the bottom, and we will see how these reversible processes undergone by the engine turns into the corresponding graphs in the TS diagram. So we can say that the corresponding to each PV diagram, you will be able to construct its TS diagram. For each PV diagram, there will be a corresponding TS diagram. Okay, so there are different ways of representing or visualizing the various thermodynamic process undergone by a system. Whether you use the PV diagram or you use the TS diagram, it can represent. And each diagram has got its own merits and its own application depending on the context that we are dealing with. Right? So if you are interested in knowing the entropy change, then better, you go for the TS diagram. And if we are just focused on the work delivery during a process, better we can depend upon the PV diagram, even though both the diagrams can give you same information. Okay, one will be suitable for one context and the other will be suitable for the other context. Okay, so let's just start. So already see, I have drawn the TS diagram for the gasoline engine in the figure C, first figure in figure C. So just have a look at the diagram before we begin with, and see that the labels that I have used here, see, like 1, 2, 3, 4, they correspond to the same labeling that we are using in the PV diagram. That will help us in comparing the two processes easily. So just have a look at the PV diagram for petrol engine that is given here. So this is the PV diagram for the petrol engine. You can see the reversible cycle. So you note the point 1. So this is the point 1. Okay, at the beginning, this is the point 1 here. Now the first process here, that is an adiabatic compression. Adiabatic compression. So the adiabatic compression is shown by this one. Remember, in our theoretical derivation or in the discussion of the PV diagram, we have been stressing that we are considering all the process to be happening reversibly. Right? All the process were happening reversibly, means it was happening at a very slow pace, at a very slow speed, almost quasi-statically, such that each point along the curve is well defined. Okay, so reversible process. So here it is adiabatic. So what is the first process from 1 to 2 representing in the PV diagram? It is representing what is known as the adiabatic compression, right? Adiabatic compression. So 1 to 2 in PV diagram, 1 to 2 was representing adiabatic compression. Let me write AC for short. That is enough, right? Remember, all the processes are reversible. Okay, reversible. And when it is reversible and adiabatic, there is a straight conclusion. What is all reversible adiabatic process undergone by a system are isentropic. That was our conclusion. Reversible adiabatic processes are isentropic, right? So the process 1 to 2, which is a curve in PV diagram, how it should appear in the corresponding TS diagram. So it should appear as an isentrope, right? It should appear as an isentrope. And you can see in the diagram, TS diagram, 1 to 2, which is 1 to 2, this is 1 to 2. 1 to 2, can you see it's an isentrope because it's a vertical line that is parallel to the temperature axis. So this is happening at some entropy. You say S1, isentrope. Is it okay? S1 means the entropy at point 1 is equal to at point 2. If you want, you can write it's S1 equal to S2. If you call entropy at point 1 as S1 and entropy at point 2 as S2, I can say S1 equal to S2, right? Okay, so this is a corresponding graph. So corresponding to 1 to this graph here, this part of the curve here, we have got this 1, 2 vertical line. Now, let's see what's the next thing. The next thing, you know, in the PV diagram, the process 2 to 3 is occurring at constant volume, which we are labeled as V2 here. So what is 2 to 3 in the PV diagram? In the PV diagram, 2 to 3, okay, that is nothing but an isocore. Isocore. That's an isocore. So it is a vertical line here. So 2 to 3 is a vertical line, and you know, during this isocoric process only, reversible isocoric process only, QH is entering the system. So in place of that, the 2 to 3, you see the diagram, TS diagram, what is 2 to 3? The 2 to 3 is represented by this particular graph. You recall this type of a graph we have seen in the previous session. 2 to 3 is an isocore. Okay, an isocore, we have concluded that is steeper than an corresponding isobar for a given system. So 2 to 3 is an isocore. It's a curve like this, which we have predicted earlier. And so it's a curve isocore. So if you want, you can just denote that this is an isocore, that is delta V equal to 0 during this process. And remember, it's during this process that the heat is entering the system. That is QH is entering the system during this particular process. Remember, so corresponding to this 2 to 3, this is the 2 to 3. Okay, now after 2 to 3, 3 to 4 in PV diagram represents adiabatic. 3 to 4 is adiabatic. Adiabatic expansion, right? This is expansion, and this one is what? Compression. So let me write here for our idea that 3 to 4 in the PV diagram is an adiabatic expansion. And being reversible, all steps being reversible, it is reversible adiabatic. What do you expect in the TS diagram? That should be an isentrope. This is isentrope. Okay, the same manner here also, this one should be what? Isentrope. There is no difference. Okay, so isentrope. So that is why you can see that 3 to 4 here is again, once again, a vertical line, isentrope. Okay. The length of the line depends upon the amount of change. Okay, so don't bother about the length of the line here in one particular diagram, but when you compare two diagrams, of course it has something to say. So this is representing 3 to 4 is representing nothing but an isentrope. This is nothing but corresponding to the adiabatic expansion, remember, and this one corresponds to the adiabatic compression. You should be able to just shift between the two curves, but the process remaining the same. Remember always that it is the same process undergone by a given working substance that is represented by two different diagrams, and that is the beauty. Okay, even though they look differently in the diagram, they are representing the same fact, right? Okay, so that is the thing. Now once again, from 4 to 1, you know, now we are coming back. It's a cyclic process. 4 to 1 in the PV diagram, you know, that is once again happening at a constant volume for a gasoline engine. So there is once again an isocoric process. So you can see that here also, that is an isocoric process. Okay, so graph is looking similar to the 2 to 3 graph. This is an isocoric process. So that is 4 to 1. So this is also delta V equal to 0. Delta V equal to 0 for this isocoric process also. And you can see it's during this stage or during this process that heat is going out. So the heat is going out of the system, working substance. So this is QL. QL goes out. And let me tell you another thing that you should understand. Can see, if at all any heat is entering, any heat is entering or heat is losing from the working substance, that can have only two windows. Either it should be entering during 2 to 3, or it should be okay, entering or leaving during 4 to 1. Why? Because 1 to 2 in the TS diagram and 3 to 4 in the TS diagram both are representing adiabatic curves, adiabats. And by the very definition of adiabats, there should not be any heat transfer. There should not be any heat transfer that occurring during an adiabatic process. So nowhere there is no chance of even thinking about some heat transfer occurring during 1 to 2 or 3 to 4. Okay, these all things you have to, these are all conceptual points that you have to keep in mind. Okay, I think this is the right time to tell you that you might have read, okay, if you have read some other extra textbooks, or you have referred to something else, you might have heard of that. Two adiabats never intersect. Two adiabats will never intersect. Okay, see, why is it so? Can you just logically argue for that? Two adiabats representing a cyclic, okay, if you are having a cyclic process, and you will never have two adiabatic curves intersecting. Why is it so? You can think of that in terms of what I have discussed right now. Okay, so like you have a PV diagram, say that this is a PV diagram, and suppose that this is one adiabat, this is the way in which a PV diagram adiabat will be there, and suppose that somebody has drawn for a PV diagram, this is yet another adiabat, and suppose that this is just like connecting them, there will be an isotherm. See that there is some isotherm here, there is some an isotherm, right? Okay, so let this be an isotherm, and this is one adiabat A1, and this is yet another adiabat. Now they are forming a cyclic curve, say. Now you can see that in this diagram I have shown that the two adiabats are intersecting. Such a thing can never happen. What is the reason? You can understand. You will see that if two adiabats are intersecting each other, then there will be a clear violation of the second law of thermodynamics. Okay, so the hint is here. I told you there won't be any heat transfer across the adiabats. So this one is having only 3 sides now. This is having a 3 sides, right? So if heat is entering through this isotherm, it can enter through the isotherm, right? Okay, now can the heat leave from here? No, there is no heat transfer across. There is no heat transfer across this one. Okay, there is no way to get the heat rejected. So if such an engine, theoretically if you presume such an engine, then you can see that there is only one heat transfer occurring. So Q in, and all this Q in should be converted into work. The area enclosed by the PV diagram represents the net work done. So with a single heat reservoir, this particular theoretical engine is producing work, and it's a violation of, you can see it's a violation of the Kelvin Planck statement of the second law of thermodynamics. So remember that. So that is one reason why you remember that all these engines are having 4 paths, right? 2 adiabats are there, and there will be 2 isotherms. Okay, that in the case of Carnot engine, we had 2 isotherms connecting 2 adiabats. So remember that fact. Okay, so I just deviated from this one. These are all facts that will be of use for you, and when we come back to our engine. So hope you understood how to convert a given PV diagram into corresponding TS diagram. Now it's quite easy for you to do the same thing with what? The diesel engine. So the only difference in the diesel engine is that process 2 to 3, which was earlier isochoric, now has become isobaric. So this is isobaric. This is isobaric. All reversible. Okay. So what will happen? 1 to 2 is adiabatic compression. So that is shown here. 1 to 2 adiabatic compression is isentropic. This is isentropic. S equal to a constant. Okay. And one thing maybe, okay, yes, just I can ask you that at the end. 1 to 2 is shown to be isentropic, 1 to 2, because it's adiabatic compression. Now 2 to 3 in the PV diagram, you can see it is shown to be isobaric. Okay, so the 2 to 3 in the TS diagram is also a curve. You can see that it's isobaric. when you compare with the 2 to 3 in the corresponding gasoline engine, you can see that its slope is shown to be a bit lesser. Okay, no need, because you can just at least to tell you that the slope of the isobaric, when you are, if you are representing, if you are comparing two graphs, see that some reduction in the slope is shown. Okay, the isobaric, okay, since it is two different systems and all, there is no scope of comparing it, but in general, remember that the slope for an isobaric process undergone by the same system will be a little bit okay, or they're having lesser slope compared to the corresponding isochoric. So this process represents that it is delta P equal to 0. Remember, delta P equal to 0. Okay, now see 3 to 4 once again, that is adiabatic expansion. Adiabatic expansion, once again, it's a what you call it's isentropic, so it's a vertical line. And see here 4 to 1. 4 to 1 is once again what? 4 to 1 is isochoric. 4 to 1 is isochoric. So this is delta V equal to 0 for 4 to 1. Okay, and here you ought to compare. Okay, 2 to 3 and 4 to 1 are the two processes undergone by the same working substance. So you should be careful while you draw their slopes. Okay, and isochoric, you can see that isochoric has shown to be more steeper than the corresponding isobaric. Okay, or isobar. So that is to be taken care of. Okay, that's clear. Here also the heat entry and the heat loss are happening during which one? During this stage, you know. Okay, that is shown here also. 2 to 3 QH is entering the system, and during 4 to 1 some heat is rejected by the system QL. Okay, and you know the area, yeah, don't forget about what we have discussed earlier. What is this particular shaded area representing in a TS diagram in a cyclic process? This shaded area will represent the net work done by the engine. Okay, the work done by the engine, and the same thing was true, you know, okay, in the case of PV diagram. So that is the importance of this particular TS diagram. Okay, and let me finish this particular session by asking you this particular question. Can you see that when you compare the gasoline engine and the diesel engine, the process from 1 to 2, if you are comparing, if it is not scaled here, but if you are scaling this one, can you see this is 1 to 2 has been shown having greater length, okay, in the case of diesel engine. Okay, the reason, I hope you remember, okay, the reason is that you know, in a diesel engine we are compressing more. Okay, we are compressing the what is that, air, right? We are compressing air because a diesel engine is a compression ignition machine. Hope you remember that we compress the air more to raise the temperature of the air to very high values, very close to the ignition temperature of the diesel, right? Then only we are spraying diesel into the thing. So this particular lengthy or just higher difference in the temperature shown in the diesel engine correspond to higher compression that is happening, higher compression. Okay, so hope that it's quite easy for you by the time to understand or interpret the TS diagram, provided you have the PV diagram which you are already familiar. So that is my suggestion for you. Whenever you are asked to draw the TS diagram for a particular engine, say it's Carnot engine, or it is the petrol or a gasoline engine, or it's a diesel engine, always have what is already with you, which is that PV diagram. And it's always advisable that you convert each of the process into the corresponding process in the TS diagram. It will help you to compare, and also it will help you to better understand how the same processes are viewed or represented by different diagrams in science in general. Okay, hope that this session was useful to you. Thank you.